Good evening.
Yes, I would like us to start. Just confirm to me that it's visible.
Yes, it's visible.
Thank you very much. So, as I indicated last time, that we are done with probability. Now we are moving to statistical inference. Basically, there are actually three areas of statistics. We have descriptive statistics, and then we have inferential statistics. This is the second branch. The third branch is called statistical decision theory. So there are actually three major areas or branches of statistics. I know you have done, of course, descriptive statistics, and then now we are studying inferential, or basically statistical inference. Actually, the probability is actually a language to be used in studying statistical inference. So probability is not actually statistics as such. It's actually a language to be used in statistical inference. That is why when it's taught as a unit, you see probability and statistical inference. So the probability is there as a tool in order to study statistical inference because of uncertainty, because of the randomness we discussed when we were to introduce random variables. So this set of notes, you realize the note 6 is typed because I started working on notes for in theory of estimation. So this is part of the notes for theory of estimation. It is work in progress. I'm still typing it, and then later on we shall move the hypothesis testing, which I have not typed yet. So as I indicated earlier, this unit comprises three major areas also: the probability, estimation, and hypothesis testing. Whereas, of course, estimation and hypothesis testing fall under statistical inference. So we are going to start so that we actually define what statistical inference is all about as we progress. So statistical inference is the process of drawing conclusions about the population on the basis of sample results. That means when you want to study a characteristic in a certain population, we usually don't take measurements of all individuals in the population. We usually take a sample, or basically a random sample. And of course, a random sample is a representative of the population. So we usually analyze the sample. And then whatever conclusions we make about the sample, we infer, or by induction, we say they are also valid in the population. So that is what statistical inference is all about. So it is like making decisions about the population based on limited information. Limited information in the sense that you have not taken measurements of all individuals in the population. You have just taken measurements of a cross section, which of course we are calling it a sample or a random sample, which represent the population. So this actually you are making decisions based on limited information. Mm. So this branch of statistics is called inferential. or inductive statistics, as it entails inductive reasoning. Because the reasoning actually is by induction. You are saying what is true in the sample is also true in the population. That's actually inductive reasoning. You're saying what is true in the sample is also true in the population. That is by induction. That is why it's also called inductive statistics. So when you talk of inferential statistics, we can also call it inductive statistics. Whereas for descriptive statistics, we shall also call it deductive statistics. Yes, as I've just mentioned that we also study probability just as a language to study statistical inference. Now, in the inference, in making decisions about the population based on the sample results, we cannot be absolutely certain. You cannot say whatever is true in the sample will actually be true in the population with certainty. Mm. So such inference cannot be absolutely certain. That is why the language or probability is used in stating conclusions. So we use probabilistic language in stating conclusions about the population based on sample results. All right. Now, so when we talk of inference, later on we shall actually define formally by stating what an inference problem is all about. Now, we want to define two important aspects in statistical inference, what we call parameters and statistics. They are both coined population parameters and sample statistics, depending whether they relate to the population or the sample. So a parameter is an unknown characteristic of a probability distribution. Of course, we have studied probability distributions whose values determine a particular distribution. So as we discuss inference, you can see this parameter we are saying is unknown, not known. Is not known. So it is an unknown characteristic of a probability distribution whose values determine a particular distribution. So when that unknown parameter takes a particular value, it actually determines a particular distribution. You actually know that distribution when that parameter takes a particular value. So knowledge of the parameter or parameters, depending whether the system has one or more parameters, fully specify the distribution. So once you know the value of the parameter, what you are saying is that you actually know that distribution. Parameters are associated with the population. So that is why we call them population parameters. Hence the term population parameters. Now, the set comprising the parameters is called the parameter space, usually denoted by uppercase omega, Greek letter omega, uppercase. This is omega, uppercase, or capital letter omega. The following examples clearly illustrate the parameters and the parameter space. So I'll use the examples now. Remember, we studied distributions, both discrete and continuous. So we are going to be using those distributions to illustrate or to explain some aspects or concepts in inference. And the parameters of these distributions, they are actually unknown. No, they are unknown. So the first example is the Bernoulli distribution. And now, because we are dealing with inference, we must actually, as we talk about Bernoulli distribution, we must say it alongside the parameter of that distribution. That's why we are writing Bernoulli distribution with parameter theta. Before, when you are studying probability, you are writing distributions saying f of x, whether x is discrete or continuous. That is, you're just saying f of x, where we know this just a probability function or a PMF when x is discrete, and a probability density function PDF when x is continuous. But what we were not highlighting when writing distributions was the parameter, because we were not really concerned about the parameter when we were studying probability. But in statistical inference, parameter is of interest. So when writing the probability distribution, when you are just writing f of x, you can see I'm actually highlighting the parameter of interest, that a known characteristic of this probability distribution. Here we are calling it theta. You will find that most of these parameters we use Greek alphabet to denote them. And I say Greek alphabet, so you know them. You know the Greek alphabet for lowercase. You know the Greek alphabet for uppercase. You also know how to pronounce them. So in the Bernoulli distribution, you can see the parameter of interest is theta. So this is actually so the distribution itself is not different from what we have studied as a Bernoulli distribution, but we are just stressing on the parameter now. Hence the Bernoulli distribution with parameter theta. Also remember, there are two aspects when writing distribution, a probability distribution. We must specify the support. That is where the function is defined. So the support of this distribution that means the values of the random variable, or where the distribution is defined. If you sum over those possible values, you'll get one. Because a probability distribution. So you must specify the support. Also, of interest now in inference, we're also specifying the set, the parameter set, where the parameter takes the values. So you can see for here, we are saying theta lies in the interval 0, 1, 0, and 1 exclusive. So we have actually a set here, which we call the parameter space, which we are denoting by uppercase omega. So we write it as a set. So you are saying this parameter space comprises values theta, such that theta lies in the interval 0, 1, 0, and 1 exclusive. And of course, the interval 0, 1 is an interval in R. So basically, it is a subset of R. And the moment you talk of R, you are talking of unidimensional set, one dimension. So also what I'm indicating very important properties of any distribution, among others, the basic ones, the basic properties of interest in any distributions are its mean and variance. We also know other properties like the MGF and so forth, like skewness, kurtosis, but I'm only indicating the basic ones, which are of interest in our usage here. So I'm indicating the mean and the variance, because the square of x is theta, power of x is theta in the 1 minus theta. So if you remember in the Bernoulli distribution, the parameter in the Bernoulli is actually the probability of success in a Bernoulli trial. It's actually the probability of success in a Bernoulli trial. One thing to note is that the mean and the variance, you find they are actually functions, or they depend on the parameter. The mean and the variance depend on the parameter. meaning actually all the properties of the distribution actually depend on the parameter. So if you are talking about the skewness, excess kurtosis, all they will depend on this parameter, or even the MGF, they will depend on this parameter. So this is our first example. The second example is the Poisson, Poisson distribution. Here we are using the parameter lambda. So you can see we are highlighting it here. And now we write, check very clearly. I write f of x semicolon and then the parameter. F of x semicolon then the parameter. You can also see f of x semicolon the parameter. So we are writing the parameter of interest. This is a Poisson. The support of the Poisson is 0, 1, 2, up to infinity. And lambda is positive. So you have the support and you have the parameter space. So specifically, the parameter space is T set of positive reals. The parameter space is the set of positive reals, which is a subset of R. More precisely, it is R plus positive reals. So here I've indicated the mean and the variance, which are of course both equal for the Poisson. So you remember the way you already distribution. We write the function, what it is, and then outside the support, we write 0 otherwise. We write 0 otherwise. So that's essentially the function we are writing is the x is basically a real number. We have exponential. I'm using the parameter, I'm using theta. And the one I've given, I'm also naming these equations because, I intend to write a book in this. So I'm numbering the equations. Like this one is saying equation 1, say in chapter 1, equation 2 in chapter 1, equation 3 in chapter 1, something like that. And also we shall be using this numbering ahead there when we want to refer to these distributions. So when we want to refer Bernoulli, we just say equation 1.1. If we want to refer to Poisson, we say equation 1.2 and so forth. So this is exponential with parameter theta. And if you check closely, this is actually exponential type 1. We also have exponential type 2, which you can check in the previous notes. So you can actually see that the parameter space, again, the positive reals. So we have the mean and the variance. Normal. So the first three, the parameter space is unidimensional because they are subset of R. So they are unidimensional. The first three examples. The fourth example is the normal with parameters mu and sigma. So this one has two parameters, meaning the parameter space will be two-dimensional. So you can see now I'm highlighting both parameters. I say f of x semicolon mu comma sigma. So you're saying f of x, the function of x. Now the parameters of interest are indicated after the semicolon, and the parameters are separated by a comma. So when you have two parameters, you write as indicated here. If you have even three, you write the three parameters and then you separate them by commas. So if you check what you have here, it's basically the normal. The support is R. You can see. For the parameter space, you can see mu is also in R, but sigma is positive. So this is how we shall write the parameter space. It will comprise of the coordinates mu sigma. So in our case here, the parameter here, sigma, as we know, for the normal is actually standard deviation, and mu is the mean. So if standard deviation is sigma, it means variance is sigma squared. So because mu lies between minus infinity and infinity, and sigma is positive, it means our parameter space is the upper half plane. So in R2, it is actually the upper half plane. You know, R2 is the plane, the XY plane. Now it is the mu sigma plane. So this R2 is exactly that plane, but you are saying now the upper half plane. So if you are putting mu on the horizontal axis, you put sigma on the vertical axis, then you find the horizontal axis mu will take minus infinity to infinity. On the vertical axis, sigma will be from 0 to infinity. So you can actually see you are on the upper half plane. Basically, also is a subset of R2. That is why our parameter space here is two-dimensional. Example number 5 is the gamma distribution. The parameters are alpha and beta. You can see, so I have here x and the parameters separated by a comma, the alpha and beta. This is the support is R plus positive reals, and then alpha and beta are positive. So you'll find that the parameter space will comprise coordinates alpha beta, where alpha is positive and beta is also positive. So basically, this is actually the first quadrant on the plane, or in R2. It is actually the first quadrant. So this is a subset of R2. So this is also an example of the two-dimensional parameter space. Those are the properties, the mean and the variance. And of course, basically, this is actually gamma type 1. This is gamma type 1. If you remember, we also have gamma type 2. Under the remark, you are familiar with this. We talk about the gamma function, so I don't have to repeat this. We talk about the gamma function, even that integral. We discussed it in the previous notes and refer to those. But the next example is the beta distribution. Maybe we not mentioned this in the as an example earlier, but this is the beta distribution. I remember mentioning it when you were studying the F distribution. This is the beta distribution. We're doing the F distribution. This is related to that. And these are our beta distributed parameters. So you can see alpha and beta are positive, but the support is the interval 0, 1. So the parameter space again is the first quadrant in R2. So is the mean and the variance. So you can see in all examples, the mean and the variance depend on the parameters. In the remark, it's just talking about the beta function. You remember? So the beta function is given as indicated here. As this integral here is called the beta function, as denoted on the right-hand side, b of alpha beta is called the beta function. And this beta function is also related to the gamma function. The beta function is related to the gamma function in this expression here. Now, we want to talk of a statistic. You see, under this section, you are talking about population parameters and sample statistics. So we have defined what a parameter is, and I've used examples to illustrate that. Now we want to discuss a statistic. So a statistic is a function of the random sample. So when you talk about random sample, as I indicated when you are studying probability, it means these random variables are IID. They are independent and identically distributed. And when you talk of random variables x1, x2 up to xn, we are talking of a random sample of size n. So a statistic is a function of the random sample which does not depend on the unknown parameter. So a statistic should not depend on the unknown parameter. We have discussed what a parameter is, and we have said that parameter is unknown. So a statistic is actually a function of the random sample which does not depend on the unknown parameter. So for it to be called a statistic, it should be a function of the random sample, but should not depend on the unknown parameter. If it depends on the random sample, and then at the same time, again, it depends on the unknown parameter, it is not a statistic. The theta we are referring to, the parameter, is actually is fixed. In our understanding here, or in our discussion here, we treat it as fixed. It's not just varying, it is fixed. A statistic is a random variable. So because it depends on these random variables, it means it is also a random variable, because a function of a random variable is a random variable, or in general, a function of random variables is a random variable. So a statistic is a random variable, since it is a function of random variables. And therefore, the values of a given statistic will vary with particular sample values. Formally, we define a random variable and the value the random variable takes. We were denoting a random variable by a capital letter, say x, and the value it takes or it assumes is lowercase x. So we have defined a function of a random variable x. Then the value that random variable will take will be a function of the lowercase x. So when a random variable takes particular values, it means the function of the random variable will also be taking particular values. Now, a statistic is associated with the sample. Hence, the term sample statistic. So that we distinguish it from the parameter, which is associated with the population. That's why we are saying population parameter. But here we are saying sample statistic, because the statistic is associated with the sample, not the population. So a statistic is associated with the sample, hence the term sample statistic. Now, from what we said in probability, where the moment you have defined a random variable, that random variable has got a probability distribution. It must have a probability distribution of whatever nature. So because a statistic is a random variable, then it must have a distribution. Now here in inference, that distribution or the distribution of that statistic is called sampling distribution of the statistic. It's called sampling distribution of the statistic. Now, before I look at an example. So when you talk of taking a random sample to represent a population, in inference, there are various ways. Remember, there are various ways of choosing a sample. We usually have what we call probability sampling and non-probability sampling. So for inference purposes, we must use probability sampling. For instance, selecting a random sample that is actually probabilistic. Like what you were saying, equally likely, when you are using a simple random sample, say all individuals are equally likely to be in the sample. That is probability, one aspect, one example of probability sampling. We don't use non-probability sampling in inference, no. Like purposive sampling, judgmental sampling, convenience sampling. We don't use such in inference. Now, let x1, x2 up to xn be a random. So anytime we talk of a random sample, remember the random variables in question are I, D. independent and identically distributed. So let this x1, x2 up to xn be a random sample from the Bernoulli distribution. You can see now I'm referring to it. If you want to go and check this, means you have to go to equation 1.1. So we have indicated that population mean is expected of x, which is theta, is actually the parameter of that distribution. So the mean is the parameter. So when you are saying it's an unknown characteristic, so that unknown characteristic, which is theta, is unknown, which is basically exactly the mean of the population. Exactly the mean of the population. It is unknown. Now, where is the sample mean? So if we are to use to say the sample, remember also when you are talking, we have talked about the sample mean when you are dealing with sampling from normal. So the sample mean x bar is the mean of these random variables. So actually this sample mean is also a random variable because it's a function of random variables. Just using this to illustrate what we mean by a parameter and a statistic. So you find that the sample mean, you can see, is a function of the random variables, and you can see it does not depend on the unknown parameter theta, then this is a statistic. And also the sample variance, you can see this sample, this is actually variance of these random variables. This is actually variance of these random variables. We are calling it S squared. And you can see it is also a function of these random variables. Meaning actually the sample variance is also a random variable. So you can see both the sample mean and the sample variance are functions of the random sample. And both of them don't depend on the unknown parameter theta. So that's why they are called statistics. So these are statistics. Whereas if I define a function, those are a function of the random sample, but it depends on theta. You can read this a random variable, yes, but it is not a statistic. So that you really understand what we mean by a statistic. A statistic should not depend on the unknown parameter. So this also a random variable because it depends on the random sample, the random variable, but it's not a statistic because it depends on the unknown parameter, this function here. So you can see for the sample variance, it talks about deviations of observations from the sample mean. But in this function I've defined, it talks about deviations of the observations from the population mean. So it has that parameter theta, which is the population mean, and it's unknown. So it depends on the unknown parameter. So this is not a statistic, though it is a random variable. Further, suppose I have taken a random sample of size 10. So my n will be 10. And if I take measurements, then this is the observed sample. So when I write with lowercase xs, I'm talking about the observed sample. So if this was a random sample of size 10 from the Bernoulli distribution, we know for the Bernoulli, the support, the random variable x takes 0 or 1. So that's why we say we are talking about a Bernoulli random variable, only two possible outcomes. So suppose we have a particular scenario that this is actually the possible scenario when you take measurements, because x's can take 1 or 0 or 1. So you'll only be having a sequence of zeros and ones depending on what the outcome is. When you have a 1, that means in the Bernoulli trial you have a success, and when you have a 0 you have a failure. So suppose it's a particular scenario. So you say the first observation is a success, the second is a failure, the third is a failure, the fourth is a success, like that, till you reach that the last is a failure, like that. So you have this kind of sequence of zeros and ones. So this is actually say this is a particular situation, then the value, you are now to get the value of the sample mean, the value it takes. That's why I was saying, because it's a random variable, we don't be taking the values it takes will depend when the sample changes, it will also take different values. So in this particular case, you can find the value the sample mean takes. These are not variable. The value it will take, you can see I'm using lowercase x here. These are now a particular value of the random variable x bar. This is a particular value of this statistic. So you'll get x bar for this particular situation here. You can see there are how many ones? 1, 2, 3, 4. So summation of xi, you get 4 divided by 10, 0.4. So a particular value of this sample mean, the value it has taken is 0.4. If there were 5 ones, then our x bar will be 0.5. If there were 7 ones, our x bar will be 0.7. So it changes also depending on the values assumed, depending on the observed sample. Similarly, you can see for the sample variance, you can take the particular value which you had. So you can see my sample variance, this is a random variable. This is why I'm writing as capital S squared. Just as this is squared for very just a notation. So the value it will take is the lowercase s squared. So if you get s squared for this particular set, you are actually say 1 over 10 sum of squares of deviations of these observations from the mean 0.4. So you'll get the particular value 0.24. So these are particular values of these statistics. Sample mean 0.4. Sample variance will take 0.24. And you can see when the observed sample changes, these statistics also will also take different values depending. Now, there's what we call an estimator. An estimator is a statistic whose values are used to estimate the value of an unknown parameter, say theta. That's when we defined earlier a parameter to be unknown. So in inference, we are interested in estimating that unknown parameter. So when you talk of an estimator is a statistic. So it means actually an estimator is a random variable. An estimator is a statistic whose values are used to estimate the value of a known parameter, say theta. That is why he was saying a statistic should not depend on the unknown parameter. Because now an estimator is actually a statistic which will be used to estimate the value of a known parameter. So if it was depending on the parameter which is not known, how would you use it to estimate a known parameter? Do not make sense. So an estimator is a statistic whose values are used to estimate the value of a known parameter. Say theta. It could be beta. It could be lambda. It could be anything. But for the sake of argument, I'm just using theta to explain this. In terms of a notation, we shall denote the estimator of theta by uppercase theta with a hat. That hat indicates we are talking of an estimator. And the moment you use uppercase, we are actually saying it is a random variable because an estimator is a statistic. Because actually a statistic depends on the random sample. So more precisely, I'm saying, so we can write this vector theta hat, or to be more precise, we indicate that it depends on the random sample. That is why we are saying it is a statistic. So we say theta hat, but specifically we indicate it depends on the random sample. Now, an estimate is a particular value of the estimator. So it is like saying we have a random variable and the value it takes. So estimator is a random variable. The value it takes is an estimate. An estimator is a statistic. So we have a statistic here, which we are using now as an estimator in order to estimate the unknown parameter theta. So when it takes a particular value, we call that value an estimate of theta. So the value of the estimator calculated from a specific sample is what we call an estimate. We shall denote the estimate of theta by theta hat. You can see for the estimator, we are writing uppercase theta hat, but for the estimate, we are writing lowercase theta with a hat. All of them must have a hat to show that we are discussing estimation. But now we uppercase theta with a hat is estimator. Lowercase theta with a hat is estimate. So the way we denoted this, the estimator, indicating it's a function of random sample, it means the estimate is a function of the observed sample. So an estimate is a function of the random sample, but an estimate is a function of the observed sample. So we should be able to distinguish between what we have discussed, the parameter and the statistic. Or to be more explicit, population parameter and sample statistic. And we have used a number of examples, and you can see that's why we was in distribution, so that when discussing inference, we have examples to use. We use distributions which we are familiar with. Now, in this next section, we want to really bring out the problem of parametric statistical inference. So you can see I'm bringing in here the term parametric. So we are talking about statistical inference, which we have discussed here, but we really want to bring in this aspect of parameter as far as statistical inference is concerned. So we are going to formulate a problem in terms of this parameter. Hence, we are going to talk about the problem of parametric statistical inference. Actually, this also brings to light what is inference actually. What is the problem to be investigated or to be solved? So it actually arises when you want to study a characteristic, even before when you are studying probability, you are saying when you want to study a characteristic of a given population, you can denote that characteristic by a random variable x. And associated with that random variable x is its probability distribution. And you can see that distribution as an unknown parameter. And because it's not known, that is now where the problem is. Because it's not known, we need to estimate it. Because it's not known, we need to estimate it. So let us start by saying, assume that some characteristic of the elements of a population can be represented by random variable x, having probability distribution f of x theta. So you can see I'm denoting the way you are writing those distributions. F of x semicolon theta. So I'm just using here for the sake of argument. Using those, if you were to use examples, we have described that parameter can take different notations, any of those Greek letters, whose form is known, except that it contains an unknown parameter theta. So you want to study some characteristic of a population, we have denoted by a random variable x. It has a distribution, a probability distribution of x theta. And you can also, we are specifying that theta is the parameter space of some kind. Yeah, like those in those examples. Because we have seen different distributions have different parameter spaces. And you are now saying the form of this distribution is known. The form, when you say the form is known, you can actually say it is, we know this Bernoulli, you know, we know this Poisson, we know this binomial, we know this exponential, we know this normal. But I'm using here with one parameter just to explain what the problem of statistical inference is, which can also be extended to many parameters. So whose form is known except that it contains an unknown parameter. So from the onset, there's a problem here because the parameter is not known. Further, assume that the values, the lowercase x's now, so this is observed sample. Assume that the values using the lowercase x is now the observed sample over random sample. You can see the difference how we are denoting. This is the random sample, but this is observed sample. This is what the random sample as taken as far as that these random variables are concerned, or the random variables have assumed these particular values, hence the observed sample. So we are saying in this we are able to have these observations. So when you say assume that the values of random sample can from f of x theta. So again, this random sample is from the, when you say from f of x theta, we are basically saying we have taken a random sample from a population having this distribution. And when you say a population having this distribution, we are saying that random variable, that characteristic of the population is what has this distribution. So simply put, you usually say a random sample from this distribution. But inherently, we are actually taking a random sample from the population having this distribution. Or more precisely, the characteristic of interest which we have denoted by random variable x as for this probability distribution. So when you are saying can be observed, it means you can actually take measurements. You can actually take measurements. You can actually have observations. Taking measurements when whatever your characteristic is x, there are various ways of taking those measurements depending on the context. Now, because this parameter is not known, so our interest is actually to estimate it. Thus, we may A, estimate the value of theta by numerical quantity. So we can estimate it by numerical quantity. That is what we call point estimation. B, find an interval in which theta will lie with a high probability. That is called interval estimation. So you want to say theta lies in this interval with this probability. And that, so that it actually lies in that interval, it must be with a high probability. With a very high probability. That is called interval estimation. C, you can actually determine the likelihood with which, say, theta is greater than theta naught, or theta is less than theta naught, or theta is not equal to theta naught, where theta naught is specified. So you can actually specify a value of theta, and then you determine the likelihood whether the true parameter theta, or the true value of the parameter theta, what is the likelihood that it is greater than the specified value, or it is less than the specified value, or basically negating that is not equal to the specified value. So this is now called what is called hypothesis testing. So in statistical inference, there are two areas: estimation and hypothesis testing, which are supposed again to be covered in your unit. And here, with reference to the parameter, that is where we are talking about here, parametric statistical inference. If I may mention, We also have what we call non-parametric statistical inference. We have what we call non-parametric statistical inference. So we have different types of statistical inference also. But of interest to us is the parametric statistical inference. So the problem of estimation deals with A and B. So we need to cover both point estimation and interval, and also C, hypothesis testing. So that's what I was saying earlier. And this unit we have probability and then statistical inference. And in statistical inference, there are these two, I can call them sub areas: estimation and hypothesis testing. Now, as far as we have discussed this formulation of parametric statistical, the problem. So as far as this unknown parameter is concerned, we have said the form of the statement is known. Is known. F of x theta is known. We know the form. You can say exponential, you can say normal, you can say whatever. But the parameter or the parameters in question, they are not known. So it is, of course, one parameter. The parameter space is unidimensional. There are two parameters. The parameter space is two-dimensional. There are three parameters. The parameter space is three-dimensional. Or in general, if there are k parameters, the parameter space will be k-dimensional. So in particular, if we are dealing with one parameter, so if theta was what is what we are using to explain this. So as far as this problem is concerned, if theta was known, there is no problem. And there'll be no inference. Then we cannot talk about parametric inference if theta is known. So if theta was known, f of x theta will be completely specified. So if theta is known, you actually know the probability distribution. Then you can just read and use it. Then there is no problem. The problem is that I cannot use this probability distribution because it contains an unknown parameter. So if theta was known, f of x theta will be completely specified, and there would be no need to make inference about it. So we are making inference about it because it is not known. Just a minute. All right. Now I want to see how do we estimate. And as I have indicated here, under A, in the problem of parametric statistical inference, we have said in A, we are going to be dealing with point estimation. And then later on, interval estimation. And then, of course, later on, hypothesis testing. So we want now to focus on point estimation. So basically, chapter 2 in this book is point estimation. So first and foremost, you must take a random sample from the distribution in question. So let x1, x2, x1 be a random sample from f of x theta and then the parameter space. So we shall be saying that all the time, because so that there is a problem. Because we must take a random sample from a population having that distribution. That distribution contains an unknown parameter theta in the parameter space. Now there is a problem because this theta is unknown. So we shall be saying that in order to anchor the problem to be solved. So the problem of point estimation is concerned with methods of using observations x1, x2 up to xn, or the observed sample, to estimate the value of theta. In a broader sense, the problem of point estimation is twofold. One is to devise some means of obtaining a statistic to use as an estimator. So we must look for the methods. We must look uh, how do we get these methods, and you can see we must use a random sample. What will be the form of the function of the random sample? That will, of course, be a statistic. And we have said an estimator is a statistic which is used to estimate the unknown parameter theta. So how do you come up with that function of the random sample? So that's one aspect, because I've said it's twofold. And two is to select criteria and techniques to compare estimators so as to find the best estimator among many possible estimators. Because we have said, we have talked about the methods. We have said to define some means of obtaining a statistic. Those are basically the methods. In the process of doing that, you might find two methods yielding different estimators for the same parameter. Of interest is to choose that estimator which we think is best. Which ultimately will give us a best estimate of the unknown parameter. So it's like uh, considering many possible estimators, we have to take the one which we consider it the best. So there are also there are techniques and criteria for doing that. In simple language, it's like saying we have to compare. We compare the estimators. Maybe they have been derived using different methods and they refer to the same parameter. Then we have to compare them. And take the one which is indicated or which we come up with as the best. Now, the methods of estimation to be considered. So the one we shall consider are three. The first one is the method of moments. You remember well, that is why in probability we discussed moments. The second method is the method of maximum likelihood, which we shall of course discuss. And the third method is called Bayesian. Now, the method of moments depends on moments. That is why it's called the method of moments. The method of maximum likelihood depends on what we call the likelihood function. And the Bayesian estimation depends on the Bayes theorem. That is why we studied the Bayes theorem. We studied the Bayes theorem, we described it in terms of events, and later on even we described it in terms of probability distributions. Here now is when we shall actually apply it in the form when it is defined using probability distributions. And you can see, we remember when we were discussing it with respect to probability distributions, it also brings in also the conditional distribution and the marginals. In that section of 2.1, at your own time, you can read about some history regarding these three methods of estimation, or to be more precise, methods of point estimation, mm, attributed to some mathematicians. You can read about the historical note. More importantly, I want to pick in these remarks that maximum likelihood estimators are superior to method of moments estimators. Maximum likelihood estimators are superior to method or moments estimators. So when you want to determine or to estimate unknown parameters, and you want good estimators, you are advised to use, if you are to say you want to decide whether you want to use method of moments or maximum likelihood, you are advised to use the maximum likelihood because they are superior in certain senses. As in cases which the methods give rise to different estimators, generally maximum likelihood estimator is to be preferred. In some instances, the two methods can actually yield the same estimator. And in some instances, they can actually yield different estimators for the same parameter, for the same unknown parameter. So in cases where the estimators are different, it's recommended that you go with the one obtained by maximum likelihood. Two, it is usually easier to determine the method of moments estimators than the maximum likelihood estimator. So even though we prefer maximum likelihood estimators, you find that it's actually easier to determine the method of moments estimators. It's very easy. Three, maximum likelihood estimators and Bayes estimators are somewhat related. As we shall see, after we have gone through the methods, we shall see how they are related. Now, we want to start considering the first method of moments. Mm. So in inference, you can see we must start with a random sample. So we must start with ID random variable. So we must take a random sample from a population. So this will always be our first element. Let x1, x2 up to xn be a random sample from f of x vector theta in the parameter space. Now, in the examples we have considered, or the one I used to illustrate to describe what a parameter space is, in some, the parameter space was unidimensional, and in some it was two-dimensional, like Poisson Bernoulli, exponential, the parameter space was unidimensional, whereas for the normal, the gamma, the beta, the parameter space was two-dimensional. Now, you can also have a distribution having three parameters. You can also have a distribution having four parameters and so forth. So in our approach, we'll consider a distribution having an arbitrary number of parameters, which we are calling K. So that when we consider these methods, it takes care of all distributions. Because here, when K is 1, we are referring to a parameter space which is unidimensional. When K is 2, two-dimensional. When K is 3, three-dimensional. So in general, we are dealing with a K-dimensional parameter space. So that's where we are denoting now our parameter. We are calling it vector theta. So this vector theta represents these K parameters. So we see the parameter space is K-dimensional. And it takes care of any possible scenario, whether this unidimensional, two-dimensional, all case. So K is just arbitrary. So we are actually saying our parameter space is a subset of Rk. This is the Euclidean space. Now, so even when we are considering, shall be told to the same story. Also, when you talk about maximum likelihood estimation, same story. We shall consider K parameters. Now, the method of moments goes like this. We shall start by considering what we call raw moments. We shall consider what we call raw moments, and these are actually the population moments. You see, when you are getting moments of the distribution, you are actually getting moments of the population. In particular, we are considering raw moments. You know, raw moments are moments about the origin. The one you are calling mu r prime. You are talking about the Earth raw moment. But now I'm using the notation mu j prime, meaning this is the jth raw moment. So mu j prime is expression of x power j. This is the jth raw moment. In particular, what you are calling mu1 prime is the mean of the what you are calling mu in general. So mu1 prime is expression of x, is actually the mean of the population. Mu2 prime is the second row moment, like that. So if you check these row moments all the time, they are actually functions of the parameter or parameters of the distribution. So in general, mu j prime is a function of vector theta. In other words, the parameters. So we want to write that functionally, that mu j prime is a function of the parameters. These are the parameters, theta 1 up to theta k. So associated with the j raw moment is the j function we are calling gj. So gj of the parameters. So you are saying what it can be different functions. So associated with the j raw moment is a function gj. That's what the function you are saying is a function of the parameter. That's why we are saying Gj, J is a subscript, and this J is running from 1 to K. So you are saying mu1 prime is associated with the function G1, mu2 prime function G2, like that. Mu K prime Gk. So they are K functions basically. So we have defined here into 2.2, we are actually having K functions, G1, G2 up to Gk. So we are done with what we are calling it what? Population raw moments as defined by equation 2.1. And because we have said they are functions of the parameters, is now indicated mathematically using equation 2.2. So we are done with population raw moments. Now we want to consider sample raw moments. These are how we denote sample raw moments. We shall use lowercase m with a subscript j, again with a prime. So mj prime. And this is how it's defined as given by equation 2.3. It is 1 over n summation of xi raised to j. And I runs from 1 to n. Then again, we have how many? There are k of them because j runs from 1 to k. And you can see in particular, m1 prime, when j is 1, you can actually see the first raw moment, the first sample raw moment is m1 prime, which is the sample mean. You can see that goes up to, you can see the first population raw moment is the population mean. You can actually see now the first sample raw moment is a sample mean and the mean of the observations, mean of the observed sample here, mean of the observed sample. Now, the method of moment says equate muj prime and mj prime. In other words, equate population raw moments and sample raw moments to obtain what we call the method of moments equations. Hmm. 2.2, we have to first to define muj prime in 2.1, and we have essentially said they are functions of the parameters as given by 2.2. And then we have defined the sample raw moments in 2.3. And then the method of moment says equate muj prime and mj prime. So because mj prime is a function of the parameters as given by 2.2, so we are actually basically saying equate 2.2 and 2.3. Equate 2.2 and 2.3. So it is like saying 2.3 is equal to 2.3, equating them, which is simply saying now in 2.2, replace mj prime, muj prime by mj prime. Replace the population raw moments by the sample raw moments. Replace the chait population raw moment by the chait sample raw moment. Hence, you have equation 2.4. So basically now we have a system. Because J runs from 1 to K, we have a system of equations. So this is a system of equations in their known parameters. So 2.4 is a system of case equations in their known parameters. Now, assuming that there is a unique solution to equation 2.4, that system, because we have a system in their known parameters, theta 1, theta 2, theta k. So you are saying if you solve that system for their known parameters, you get a solution. The solution will give you the estimates. So assuming there is a unique solution to equation 2.4, the method of moments estimates are the solutions. In other words, it's just like saying solving 2.4. In a simple language, you are saying make thetas the subject. That means you are actually solving them. You can see here, mj prime is a function of the parameters. So to say to solve this 2.4, solve for the thetas, that means thetas will be functions of mj prime when you solve. It's like saying make thetas the subject of 2.4, meaning make thetas would essentially they'll be in terms of the mj primes. So these are the solutions. So after you have solved, you will get your theta chase. And then because they are estimates, our notation demands that we must put a hat so that it indicates it is an estimate. So we write theta j with a hat, meaning this is an estimate of theta j. So we have the estimates for the unknown parameter theta 1, theta 2 up to theta k. Is theta j prime because j also runs from 1 to k. Now, if you see, so you can see, as you infer this, in other words, as you solve, you can see that theta j will be in terms of mj primes via some function I'm calling hj. Because also there can be different functions for the different parameters. So you also have these functions h1 up to hk. They can be different functions. They will be different functions anyway. So essentially, you know, our mj primes, are functions of the observations, the xi's. So they are functions of the observed sample. So essentially, we are actually saying the estimates are functions of the observed sample because the raw moments are, you see, through this equation here. You see, we are actually using observed sample here, powers. These are powers of the observed observations, xi's. Now, so 2.5 is the estimate of parameter theta j, which we are calling theta j hat. So this is what you are calling the observed sample, in short, as vector lowercase x. Now, this is what we are calling estimate. We remember our notation, say we use lowercase theta with a hat. But for the estimator, we shall use uppercase theta with a hat. So here we shall use uppercase theta j. So theta is uppercase with a hat. So we are just, so functionally, an estimate and an estimator, they are the same functionally. But the estimator is a statistic. That is why you find now inside here, they are capital mj primes. You know, these are capital mj primes. Which basically means these lowercase mj primes are functions of observed sample, whereas capital mj primes are functions of the random sample. So you can actually see this is a function of the random sample, meaning that the j hat is a random variable, is a statistic. Now, let us look at this remark here, very important. The method of moment estimators are not uniquely defined. That is actually one of its disadvantages is a method of estimation. Method of moments estimators are not uniquely defined. The method of moments equations given, these equations given above, they are actually based on the first k row moments. The first k row moments. In fact, central moments, which you can now call mu j. Remember what you are calling mu r. Here we are now calling mu j, the j central moment. Central moments mu j. So these are moments about the mean. Rather than raw moments could also be used to obtain equations, whose solution would also be produce methods of moments estimators. So when you use raw moments, we get what we call method of moments estimators. When we use central moments, we also get what we call method of moments estimators. So they are not uniquely defined. Also, so you can see again, we have used the first consecutive k moments. They need not be consecutive. Also, moments other than the first k could be used to obtain estimators that would be labeled method of moments estimator. So they need not be consecutive. So long as you have picked care of them. That is what I meant by saying they are not uniquely defined. So this is one disadvantage of this method. We want to look at examples now. So the whole idea is very simple. Obtain the method or moments equations and solve for the parameter or the parameters, and you are done. In doing so, 2.5 tells us you will get the estimate or estimates, depending. Once you have the estimates and you want to write your estimator, as where we have just said that the two are the same functionally. This is where you see here you have the function is HA here, the function is here is HA. Where they differ is that this is observed sample, this is a random sample. So once you have an estimate, you can readily write the estimator by just making it a random variable. And you are done. So you can see, depending on the number of parameters, if you have one parameter to estimate, you only need one equation. Very easy to solve. If you have two parameters, you need two equations. If you have three parameters, you need three equations. In general, if you have k parameters, you need k equations, and then you solve for their non-parameters, which we have done to say, we have handled such problems in the past many times. So let us look at examples now. As I've just indicated, all the time we must take a random sample. So we are taking a random sample of size n from the Bernoulli distribution. If you want to see it, so I have not put here. When you are writing a book, you don't repeat equations. Like now, I've said Bernoulli distribution 1.1. So you just go, if you want to refer, you just go to 1.1. You see that's Bernoulli distribution. That is why I indicated the basic properties, the mean and the variance. Once you have the mean and the variance, it's like we have indicated the first and the second row moments. The first and the second row moments. So those two, the first and the second row moments, will suffice to find the method of moments for distributions with one parameter and for two parameters respectively. Of course, for the one parameter, you won't require one equation. So you actually require the first row moments the population, raw moment, and the sample. For two parameters, you require the first and the second for both population and the sample. So you can see for one parameter, you are just dealing with solving making theta the subject of that equation. That is actually what solution is all about. For two parameters, you have two equations, meaning you have to solve the two equations simultaneously. So you know how to solve equations simultaneously. In this example, for the Bernoulli, only one parameter theta. So we only require m1 prime and mu1 prime. So we require the population mean, the mu1 prime, which is our mu. In our case, it is theta. And m1 prime is actually x bar. So we are actually saying equate m1 prime and mu1 prime. But mu1 prime is mu, the mean of the population, which is theta. That's why he was saying all the time the mu1 prime or the mean is a function of the unknown parameter. That's why he was saying the function here is g. And because there's only one parameter, we don't have to we don't have to call it g1 because we don't have to distinguish from any other function. So we just say g of theta. Then this is now the method of moments equation, just one equation. Then say solve for theta. Make theta the subject. And essentially there is nothing to solve here because you can see already, it is already, theta is given. Theta is already a solution in itself. There is nothing to solve. Theta is basically m1 prime and we are done. So there's nothing to solve in that equation. Theta is already indicated as m1 prime. You are supposed to make it a subject, but it is already there. You only need now to write it with a hat. And the method of moments estimate of theta, now we write theta with a hat. So which is m1 prime, which is x bar. So we are saying x, the estimate is the mean of the observed sample or mean of the observations. And we are done. If you go again for the Poisson, this question 1.2 Poisson parameter lambda. So we require the population mean. So mu1 prime, which is mu for that distribution is lambda. Remember, we are using mu all the time to denote the mean of the population. That was what you were using in probability, mu. And sigma squared was variance of the population. So those are usually standard notations for the two, the mean and the variance. So here, m1 prime, we are equating to mu1 prime, and mu1 prime is lambda, the mean of the population. That's why we were saying it's a function of lambda. The function, this is a function we're talking about, g of lambda. There's nothing to solve again. There is nothing to solve. So, and the method of moments estimate of lambda is again x bar. There's nothing to solve there. So this is straightforward. Exponential 3, 1.3. Remember it was type 1. Question number 3 was exponential type 1, there is also type 2. So we require mu1 prime for that distribution. That is the mean of that distribution is 1 over theta. You can check in 1.3, this mean. So equate to m1 prime. So the function here is we're talking about g of theta. So this is the method of moments equation. Now solve for theta, make theta the subject. So if m1 prime is 1 over theta, so you solve for theta means theta is 1 over m1 prime. So that is the estimate of theta. You have now solved that equation. So that you have to indicate now with a hat. So theta hat is 1 over x bar. So theta hat is 1 over x bar. That is the estimate for theta in exponential. type 1. Example number 4, normal distribution. You can see equation 1.4. So we require two equations here because there are two parameters. First and foremost, you need the mean of the population, the mu1 prime, which is mu. For the normal, the parameter itself is mu, which is the mean of the population. Also, we require now mu2 prime, the second row moment. But the second row moment is variance plus the square of the mean, because variance is the second row moment minus the square of the mean. So the second row moment is variance plus the square of the mean. So these are the two equations. So what we meant by saying they are functions of the parameters, we are saying these are the functions here. We are saying mu1 prime is a function of mu and sigma. The function is g1. Also, mu2 prime is a function of mu and sigma. The function is g2. So you can see these are different functions. G1 of mu sigma is mu. But G2 of mu sigma, you can see is sigma squared plus mu squared. That's why I was calling those functions Gj, because they are different functions. So we are now saying here, solve for their known parameters. Solve for mu and sigma simultaneously. So when you solve for mu and sigma, these are the solutions. You'll find that mu hat is x bar and sigma hat. If you solve for sigma, you'll find that it is actually the standard deviation. It is a standard deviation of the observations. So simply put, the population mean mu is method of moments, is a sum of mean x bar. And the population standard deviation sigma is estimate is the standard deviation of the subsample observations. Solve this simultaneously. These are the solutions given by Tute. As a remark, maybe say your interest is to estimate sigma squared and not sigma. So what it means, just solve for sigma squared in these equations. You will get an estimate for sigma squared. So you'll find that an estimate of sigma squared is a sample variance. So that's why we are calling now this, so you can see we are now calling sigma squared hat. We have solved for sigma squared in these equations, meaning we have found an estimate for sigma squared, which we are calling now sigma squared hat. And if you check, it's actually the sample variance. The working is here. Just make, you see what in solving for mu, it is already there in the first equation. So when solving the second equation, wherever you have mu, you must put mu1 hat, which is x bar, when solving. There's an exercise for you here. So in the exercise, without mentioning it, one has taken a random sample. We take a random sample of size n from these distributions. So when you write like this, uniform over the interval 0 theta. This is the rectangular distribution or the discrete uniform distribution. So you should know how to write its density. So uniform over the interval 0 theta, theta is positive. So I've said show that the method of moments estimate of theta is theta hat is 2x bar. It's a sure problem, show that. So essentially, this is an estimate. This is an estimate. If you want to write an estimator, we only need to make this random. So an estimator will be 2 times x bar, capital X. This is estimate. They are the same functionally. We said here they are the same functionally. Isn't it? They are the same functionally. You see HJ, HJ, HJ. These are function of subsample. These are function of the random sample. So once you have an estimate, you just need to write the estimator. So that's why I'm only saying just find the estimate. Then automatically we know the estimator. In number 2 is uniform over the interval theta 1, theta 2, where theta 1 is less than theta 2. So you write that density, and then you show that the method of moments estimates of theta 1, theta 2. So you solve. So you need to know. So first and foremost, you need to know the mean and variance of this distribution, or simply put, you need to know the first and the second row moments. But once you know the mean and the variance, you have the first and the second row moments. Similarly for this, what is its mean and variance? That will lead you to know its mean, which is the first row moment, and the second row moment. Those you require so that you formulate your two equations, solve them simultaneously, and these are the solutions. Here, x bar is the mean of the observed sample, and lowercase, these are both lowercase, is the sample mean of the observed sample, and S is the standard deviation of the observed sample. In 3, I've said uniform over that. And so for the support, x text values in this interval indicated here. And you are told that theta 1 and theta 2 are positive. Show that the methods of moments estimate of theta 1 and theta 2 are basically the sum of mean and standard deviation. Show that the method of moments estimates are, so you can see this is uniform over this interval, right? The density also. What is its mean? What is its variance? So you should know how to write the mean and variance of any uniform distribution. The way you are saying uniform in AB, remember. So you are saying uniform in AB, here A is 0, B is theta. Here A is theta 1, B is theta 2. Here A is theta 1 minus theta root 3. B is theta 1 plus theta root 3. Like that. And we talked about uniform in AB. It's one of the examples when you're doing probability. Number 4, geometric distribution. We also talk of geometric. Now, find the method of moments estimate of theta. So you must know its mean. You must know the mean of this distribution. You should be able to get its method of moments estimate. This geometric. There's what we call location exponential. This kind of truncated. This called like truncated exponential. You know, the exponential usually takes, for the normal exponential, the ordinary exponential takes values for positive reals. But you can see this one is exponential, but takes values greater than theta, where theta is greater than 0. This is what we call location exponential distribution. In fact, theta is what you usually call the truncation parameter. So you need to find the mean. You need to, because there's only one parameter here, just like 4. One parameter, you need the mean of this distribution, which is actually the first row moment. You equate to the sample, you equate to M1 prime or X bar, then you solve for theta. That will be the method of moments estimate of theta. And once you have the estimate, we can write the estimator. But you get it specifically this exercise, I'm asking for the estimate. But inherently, once you have the estimate, you have the estimator. So you need to find the mean. You need to find the mean of this distribution. Remember, 4 is discrete. Let's see if 4 is discrete, but 5 is continuous. You need the mean for both. They are one parameter in both. Solve for theta, you'd get the method of moments estimate. So I've said find. So we are done with the first method. We have looked at the examples, and we have an exercise, 5 of them. The first 3 are sure. The last 2, you need to find them. And once you have found them, compare among yourself whether they are correct. You compare, say, 3 or 4 people, and you are getting the same thing, you cannot be wrong, all of you. But the most important thing is to do them fast. You can now see why we are doing probability. Our second method, the method of maximum likelihood. As I indicated earlier, we have considered distribution having k parameters, so I don't have to repeat that. So we have taken a random sample from f of x vector theta. Vector theta is k-dimensional. Now we have to define what we call the likelihood function, because we indicated earlier that maximum likelihood estimation depends on the likelihood function. So we have to define what is a likelihood function. So the likelihood function of the observed sample. So when you talk of likelihood function, we define it for the observed sample. And the definition is given by equation 2.11. So we denote the likelihood function using the capital letter L. And you can see it is a function. You can see here we have inside it, we have vector x lowercase, meaning observed sample. That's why we were saying likelihood function of the observed sample. That is why we write here, there's observed sample here. And in it also, it has vector theta. That's why we were saying L vector x semicolon vector theta. We didn't need vectors here. So you are saying product of f of xi vector theta, I equals 1 to n. Remember, in the random sample, they are IID. So basically, this f of xi is actually the marginals of xi's. So it's like multiplying the marginals, you know. So you can see, multiplying now the marginals. And again, they are identically distributed. So this f of xi, they are just the same. Now, equation 2.11 defines both the probability distribution function of the random sample. It has got 2 interpretations. 2.11 equation 2 defines both the probability distribution function of the random sample, this vector x, and this capital, and the likelihood function of this observed sample. So as a probability distribution, it is related to the random sample. And as likelihood function, it relates to the observed sample. How do we distinguish the two? The distinction between these functions is which variable is considered fixed and which is varying. The variables I'm referring to are the vector x and vector theta. So which one is fixed and which one is varying? Now, it is interpreted as a probability distribution function when vector theta is considered fixed. The parameters are fixed. And vector x is a variable. Whereas it's interpreted as likelihood function, which is now of interest to us. So like in probability, when we are talking about now the joint distribution of the random variables, which is actually, you can call it distribution of the random sample, here in 2.11, the parameters are fixed. Then it becomes a probability distribution of the random sample when the vector data is fixed, or simply put, when the parameters are fixed. On the other hand, it is interpreted as a likelihood function when the observed sample is considered fixed and vector data is varying. Where is it varying? It is varying over the parameter space. So you have said the parameter takes values the parameter space, or actually the parameter space defines the values to be assumed by that parameter. So that's how we distinguish the two. And this is the same function given by 2.11. In the current context, if it were just discussing probability, we look at theta as fixed. Then we look at x as varying, as a variable. But now in estimation, this of some sample which is fixed. And then we say the parameters are varying in the parameter space. So that when we are looking for the estimates or the maximum likelihood estimates of these unknown parameters, we are actually asking ourselves, we want to look for those with the highest likelihood. That is why we're talking about maximum likelihood. That will locate the point at which the likelihood function is a maximum. And hence the estimates, which we call maximum likelihood estimates. Furthermore, although 2.11 is a function of variable x, or as a function of x is a probability distribution. That means when the x is a variable, the parameters are fixed. That is what we know it is actually a probability distribution. And from 2.11, we're actually saying the product of the marginals gives us distribution of the joint, or gives us joint distribution of these n random variables, or basically the random sample vector x capital. So although 2.11 is a function of observed sample, is actually a probability distribution. That one, it is guaranteed. There is no guarantee that as a function of vector theta, it is a probability distribution over the parameter space. No, there is no guarantee that it is. It's just called a likelihood function. So as a likelihood function of the observed sample, because it is theta which is now varying, there is no guarantee that is a probability distribution over the parameter space. No. Just gives us the likelihood. Now, in statistics, this is very important across in statistics. There's what we call the likelihood principle. So in statistics, the likelihood principle is the proposition that given a statistical model, all the evidence in a sample relevant to model parameters is contained in the likelihood function. In statistics, the likelihood principle is the proposition that given a statistical model, you see, when you have a statistical model of interest are the parameters of that model, even a probability distribution is actually a model. the statistical model. So given a statistical model, all the evidence in a sample relevant to model parameters is actually contained in the likelihood function. So we're saying all the evidence is actually in the likelihood function. In other words, this likelihood function actually summarizes the sample. So the information in the sample is summarized and contained in the likelihood function. In this sense, therefore, the likelihood function can be used to summarize data, the summary measure. In other words, we call it a data reduction device. We call it data reduction index. When you are dealing with a random, when you are dealing with a sample with n observations, and then all that is summarized to one function, a likelihood function, you have actually reduced your dimensionality. We have reduced your dimensionality. That's why we call it a data reduction device. So the likelihood principle assumes that the true parametric model for the data is known. The way he was saying, we know the form of the distribution, but we don't know the parameter. So as a statistical model, we know the model, but we don't know the parameters of the model. The likelihood principle specifies how the likelihood function is utilized as a data reduction device. More precisely, if factor x and factor y are two sample points and there exists a constant c, which is a function of those sample points, and this constant does not depend on the parameters, say that the likelihood function of sample point factor x is that constant times the likelihood function of factor y for all the parameter space, then the same inference for theta should be drawn from x and y. So we are saying if the two likelihood functions for the observed sample x and the observed sample y are related by equation 2.12, we can see we are actually saying one is just a constant times the other one. The likelihood function for x is that constant times the likelihood function of the other one. And this constant depends on the sample points, but does not depend on the parameters. Then you are saying you draw the same inference for theta using the same sample point. They will yield the same inference. In other words, you will end up with the same conclusion. You will end up with the same conclusion. Or simply put, you'll get the same estimate functionally. In particular, if that constant, if this constant is 1, you can see what 2.1 says, the two likelihood functions are equal. That means the two sample points contain the same information about theta. In particular, there's a particular case, it actually says if this equals to 1, it actually says the two sample points contain the same, because they have the two likelihoods are equal, they have the same. Further, even if two sample points are proportional likelihoods, because 2.12 talks about now proportional likelihoods, because you are saying one is a constant times one is equals to a constant times the likelihood of the other one. We are talking about proportional likelihoods. Then they contain equivalent information. You may not say exactly the same, but they are equivalent. They mean the same thing about theta. In point estimation, the likelihood principle implies that the 2-point estimate. So if we were to use observed sample x, we'll end up with this estimate here, vector theta hat, which will be a function of the observed sample x. And if we are to use observed sample y, we'll end up with this estimate vector theta hat as a function of observed sample y. So this should be equal. This estimate should be equal. So in point estimation, the likelihood principle implies that the 2-point estimates should be equal. Now, the likelihood function is typically a function only of the unknown parameters. Even though we have written 2.d, even though we have written 2.d, what is it? 2.11, you can see it has vector x here and vector theta. Because we have said as a likelihood function, vector theta is fixed, but vector theta is varying in the parameter space. So because vector theta is fixed, 2.11 says as a likelihood function, L is basically a function of the parameters. It's a function of vector theta for given vector x. So this is what I'm trying to say here. That the likelihood function is typically a function only of the unknown parameters. That is when we have said vector x is fixed. So vector theta is varying in the parameter space. So we are actually saying L is, so in the context of defining a likelihood function, we are saying L is a function of vector theta. So that is for a given observation vector x, we can actually rewrite 2.11, which we are saying L of vector x, semicolon vector theta, we can just write L of vector theta to say essentially it's actually a function of the parameters. So in our context, when estimating, we shall write our likelihood function 2.11 just as L of vector theta. We know vector x is fixed. So we are saying L of vector theta is a real valued function because vector theta is in the parameter space. It means L of vector theta is a real valued function defined on the parameter space. So mathematically, we are saying the domain of the likelihood function is the parameter space. The domain of the likelihood function is actually the parameter space. Now, the likelihood function is used to compare the plausibility of various parameter values. For instance, look at equation 2.13. Suppose I say L of vector theta star is twice L of vector theta double star. Then we are actually saying theta vector theta star is twice as plausible as vector theta double star. Now you are looking for that theta which can correctly explain your sample. Because we have defined a likelihood function for the sample. So here the sample is fixed. But now we are saying we have vector theta star and we have vector theta double star. You know, this is a likelihood function. So we are actually saying vector theta star is twice as plausible as vector theta double star. And you are saying it's more likely that our theta will be given, our vector theta will be estimated by vector theta star than by vector theta double star. Because you say L of vector theta is twice L of vector theta double star. So vector theta star is twice as plausible as vector theta double star. There's a reason why I'm using the word plausible. So the word plausible is used rather than, I don't want to say twice as probable. You know, the moment you say probable, that means you are dealing with probabilities. And we are said earlier, I indicated earlier, this L, as far as theta is varying in the parameter space, there is no guarantee that it's a probability distribution. So we are not allowed to use the word probable. So I've just used the word English to say plausible. Something to be believed, it makes sense, that which exactly makes sense. eh, that vector theta star is twice as plausible as vector theta double star, so that we don't make mistakes using the wrong terminology. If we say probable, we can be very misleading, because when you talk about probable, it's about probabilities. So there is the reason, because there is no guarantee that L of it is a probability over the parameter space. Now, for discrete X, I want to distinguish the two now. And remember also the way we can write a distribution when X is discrete, we just said probability X equals small x. It gives us exactly a probability distribution. Now, for discrete X, L of vector theta gives the probability of obtaining the subsample X as a function of vector theta. You see, that's what I'm saying. It's the same function 2.11. That's why I'm calling it probability for the subsample X. This way, as a function of theta. It's the same function. Exactly. So exactly the way we have just denoted, but basically it's exactly the same function 2.11. The same function. So for discrete X, L of theta gives the probability of obtaining the subsample vector X as a function of vector theta in the parameter space. So this is the information provided by the Legendre function about the parameter theta. You see, the information is contained about theta is actually contained in the observed sample. But the sample has been summarized and given, and the summary is the Legendre function. So this is the information provided by the Legendre function about the parameter. So we are tracking that information which was contained in the sample about the parameter. It is now contained in the Legendre function, because we have said the Legendre is used as a data collection device. The summary. Now, if we compare the Legendre function at two parameter points, for instance, say vector theta star and vector theta double star, and find that the probability that the random sample takes of subsample given vector theta star, which is actually, that is actually the Legendre function, L of vector theta star. If this Legendre function under of vector theta star is greater than the Legendre function for vector theta double star, then this is actually the probability that the random sample is equal to subsample given that parameter, vector theta double star. Then we are actually saying 2.14 says the subsample X, because here it relates to the subsample X, is more likely to have occurred if our parameter vector theta is vector theta star than if vector theta is vector theta double star. This is what it says. It is more likely. That's what we about the likelihood function. Higher likelihood is more likely to have occurred if vector theta is equal to vector theta star, because this probability, which is a real function, is greater than the one we have on the right-hand side, which relates to vector theta double star. In other words, we are saying vector theta star is more plausible value, or the true value of vector theta, than is vector theta double star. is more plausible value. So because I'm looking for an estimate of factor theta, then I will take the one which is more plausible. I'll go for factor theta star than for factor theta double star. Now, the likelihood for continuous x, there is also a similar explanation, but it's a bit tricky. The likelihood function does not have a simple intuitive explanation, because this probability, if we are to get probability that the random variable x is equal to a particular value given the parameters, is always zero. If x is continuous. Remember, I said the probability that a continuous random variable takes a particular value is always zero. Meaning the probability that the random sample takes a particular subsample, which is actually this likelihood, will always be zero, always. However, we can take a positive real number epsilon and define the event that the random variable x takes a value in the epsilon neighborhood of x. So that we say x lies takes a value in this interval, x plus epsilon and x minus epsilon. This is what we call this in math epsilon neighborhood of x. And then we are going to use what we call the mean value theorem of mean value theorem of calculus. So the probability of getting a value of x near small x, that means you are actually saying the probability that x takes values in the epsilon neighborhood of x is the whole idea. Then remember how you are getting for continuous x, how you are getting probabilities. We only need the CDF. Remember, you mentioned the CDF. You are saying probability x between in the interval AB. You're just saying f of b minus f of a. So we are just going to say f of x plus epsilon. F is the CDF. Remember, the lowercase f is the BDF now. So f of x, lowercase f of x theta is the BDF. So capital F of x theta is a CDF. So just say f of x plus epsilon. All the time we must indicate the parameter because it is inference, as I've stressed. So f of x plus epsilon indicate highlight the parameter minus f of x minus epsilon indicate the parameter. Now, what you are invoking here is actually mean value theorem. So this approximately equals to twice epsilon and the derivative of f evaluated at x. Remember, x lies in this interval now because we are talking about epsilon neighborhood of x. So x is taking values in that interval, x plus epsilon and x minus epsilon. So if we remember the mean value theorem, we'll be talking of a derivative of a function evaluated at a value in the interval. The interval is x minus epsilon and x plus epsilon. Then you divide by the length of the interval. And then the length of the interval here is twice epsilon. Actually, twice epsilon. So you are actually saying f prime of x, where x lies in the interval x minus epsilon and x plus epsilon, is equals to f of x plus epsilon minus f of x minus epsilon divided by the length of the interval, which is twice epsilon. So we shall be able to relate. We have it as an approximation. yeah, because we are talking about in neighborhood. So we're talking about, and it will be approximately equal to that. But because we are dealing with a coordinate or random variable, the derivative of the CDF is the BDF. So we are actually saying to get a probability that the random variable x which is continuous is near x. So we cannot talk of it being equal, because being equal is 0. It should be near x. Would be approximately twice epsilon divided by the BDF evaluated at x. This is the BDF itself, 250. So I'm explaining here. These are in the remark, just to is kind of a recall. So what you have in the remark is kind of a recall about the CDF. This is what we did in the probability. So just for you to recall, this is what you are calling the cumulative distribution function, the CDF. We said this, the derivative of the CDF is the BDF before. So recall, but you see, then we are not indicating that the parameter because we were not doing inference then, but we are using this idea here. Again, this is the mean value theorem, which I think we even used it sometime not long ago. Mean value theorem of differential calculus. We have used it. We even have it in some notes. So this can be used that we are not talking about probability of getting a value of the random variable or the random sample near observed sample now, which is this probability. Because xi's are independent, that's why we are multiplying these probabilities for the individual. That's why we are multiplying these probabilities. Product of the individual. We are invoking here independence. So the probability of getting a random sample near observed sample will be a product of these probabilities. Independence. All right. But now we are using now what we have found here. That probability of getting a value of x near small x is approximately twice epsilon the BDF. So then to get for the xi is the same story. So this will be, this whatever I have here is approximately twice epsilon the BDF of xi, which is this one. So we have the result there. So we are multiplying. But you see here, twice epsilon does not have an I, so I'll raise to n. Then I multiply out f of xi. But from my 2.11, this is the likelihood function. So we are saying probability of getting a value of the random sample near of sample is approximately twice epsilon raised to n times the likelihood function, which is 2.16. So you find that the result with this probability is actually proportional to the likelihood function, but is a constant. That is, the approximate probability of getting a random sample near the observed sample is proportional to the likelihood function. That is what 2.16 says. Now, in view of this equation which we have found, 2.16, if probability of getting a value of the random sample near observed sample given vector theta star is greater than probability of getting a value of the random sample near observed sample given vector double star. But this one is approximately given using 216. The left-hand side is approximately twice epsilon raised to n L of vector single star. And I'm using that, this one. Because the vector in question now is vector single star. When you're on the right-hand side, we are using vector double star. So this will be approximately twice epsilon raised to n L of vector single star is greater than, this quantity is approximately twice epsilon raised to n L of vector double star. Oh, but now twice epsilon raised to n is appearing on both sides. You can cancel. So it will actually mean L of vector single star is greater than L of vector double star. So we have got a similar argument the way we did for, just like for the discrete. So again, you are simply saying it's more plausible that theta is given by vector theta is given by vector theta star than a not vector double star. So if you are looking for a value, the true value of vector theta, you will go for vector single star and not vector double star. That is explanation. Now, in parametric inference, L of vector theta is now the likelihood function can be thought of as a measure of how likely. Now I'll talk about it in quotes because it may not be interpreted as a probability all the time. We could interpret it as a probability if x is discrete, and we could interpret it as approximate probability when x is continuous. So how likely theta is to have produced of subsample? So how likely is it that this theta actually produce this of subsample vector x? Actually, your subsample is the evidence, and your sample is a fact. You are saying in statistics, let the data speak. You know. So whatever the sample is going to say is what you'll go. So what your sample will tell you through the likelihood function is how you locate your theta. So you say, how likely vector theta is to have produced of subsample? You know, your sample is the evidence now. And hence, we need to find the value of vector theta which maximizes. We don't know how likely, then we really want that theta which, when we evaluate it gives us a maximum likelihood. You now see why the name maximum likelihood doesn't matter. We need to find the value of which maximizes L of vector theta. That is, which maximizes the likelihood function. So the maximum likelihood estimate of vector theta is defined as the value, we shall call it vector theta hat, same notation as before, of vector theta. So this is now an estimate of which maximizes the likelihood function. So what it means mathematically, if we evaluate the likelihood function at that estimate, we shall get L of vector theta hat. So because L vector theta hat is the maximum likelihood estimate of vector theta, then that likelihood that evaluated at that estimate should be greater or equals to the likelihood function for all vector theta in the parameter space. So it should be a maximum. Then we are actually saying vector theta at best explains the subsample. It is consistent. The value of that vector theta is now consistent with the subsample. That's why you go with it. In other words, the value of the parameter vector theta that is more likely to have produced of subsample. Simply put, to get the MLE now, you just need to maximize the likelihood function. So we end up with a maximization problem. Maximize the likelihood function. So maximize L of vector theta. Look for the point where L of vector theta is a maximum. That is the whole idea. So since L of vector theta has been evaluated at observed sample X, generally the maximizing values of the parameters will be functions of the observed sample. That is, the maximum likelihood estimates are actually functions of the observed sample, as in equation 2.19. So they are just functions of the observed sample. So I capture my functions again. I'm using HA because there can be different functions for the different parameters. And once I have the estimates, to write the estimators, as I've indicated, they are the same functionally. You just need to write them as random variables. So 2019 and 220, they are actually the same functionally because you can see you have got HA. What you can see here is lowercase, which is the observed sample. But in 220, it is a function of the random sample. So in 220, it is a random variable. What you're actually calling a statistic. So the problem boils down to maximizing the likelihood function, or trying to locate the function, trying to locate the point at which the likelihood function is a maximum. So it's actually a maximization problem. And we do that all the time in calculus. Look for the point where a function is a maximum. Mm. Now, let us see the problem now of maximizing the likelihood function. One, we can actually transform the function itself. To simplify the maximization, we can transform the likelihood function by taking the natural logarithm. We get the log of the likelihood. Because we know the log function or the logarithm is a monotonic increasing function. A monotonic increasing function is a function you can say it is non-decreasing. It is non-decreasing. So because it's monotonic increasing, you will find that for such functions, the value of vector theta, which maximizes the log, which is the transform likelihood, is the same value which maximizes the likelihood. So if you are to locate the value at which L is a maximum, it will be the same point where the log of L is also a maximum. Well, what is more interesting here, and is to our advantage, is that the log L, the transformed log, it is easier to maximize log L than L. And since they locate the same point, then it will suffice for us to maximize log L, to take advantage of that simplicity. To take advantage of that simplicity. So the bottom line here is to look for the maximum likelihood estimate of vector theta. We all need to maximize the log likelihood. Look for the point where the log likelihood is a maximum. So it boils down again to a calculus problem. It boils down to a calculus problem. Thus, The point factor theta hat, that is now our estimate for factor theta. So now I'm talking about estimate of factor theta. Remember, factor theta is k-dimensional. So I say factor theta hat is an estimate of factor theta. So basically, we are actually saying theta 1 hat is estimate for theta 1. Theta 2 hat is estimate for theta 2, like that. Theta k hat is estimate for theta k. What k? Theta, factor theta is k-dimensional, the way we defined earlier there. That's the point factor theta hat. This is now the estimate. Where the likelihood is, this is what we are trying to locate. Where the likelihood is a maximum is actually a solution of the k equations given by 2.21. Simply put, differentiate the log L with respect to the parameters partially and equate to 0. Differentiate the log L partially. You understand what I mean by partial differentiation? Equate to 0. So basically here you have got a system again. You have ended up with a system of k equations in their known parameters. Solve for their known parameters. And the solution gives you the MLEs. As simple as that. As simple as that. What we have spent time here was to understand the logic behind getting using a maximum likelihood as an estimate of theta. The explanation is probabilistic. As for the method of moments, we are just equating population moments and sample moments. And then for maximum likelihood, we can see, trying to see which one explains the observed sample. Which one says, which theta tries to say that the distribution, what was a parameter which is consistent with the observed sample. Because I've said our observed sample is our evidence. It is a fact. Now we have to look at examples. So in these examples, we are just basically maximizing the log likelihood as given by equation 2.1. So get the first steps. Step 1. So you have said we know the form of the distribution. So we shall be able to write the distribution. 2, get the likelihood function. Step 2. Step 3, get the log likelihood. Now look for the point where the log likelihood is a function using calculus methods. First and foremost, we have to use calculus methods. We will see in a moment that calculus methods can also fail. Of course, with calculus, what it assumes is that the point at which where the function is a maximum, that function must be continuous at that point. That function must be continuous there. So this is the assumption of the calculus. But there are instances when an MLE, the point at which an MLE, the function is continuous at the point where it is a maximum. So calculus methods will fail there, and we shall see what to do. So let us see. I'm using the same examples where we found the method or moments estimate. Like example number 1, the Bernoulli distribution. We want to find the maximum likelihood estimate of theta. Because actually, so we know the distribution, the form is given by equation 1.11, the Bernoulli. We are getting the likelihood. I've seen in our context now, we're writing the likelihood. We don't have to indicate x, the factor x, because we have said the domain of L is the parameter space. So we just write as L of theta. We know this for given x. but we have suppressed that of subsample because we know this for fixed vector, if it is for fixed of the sample is fixed. So as a function, this just the domain is the parameter space. So just write as L of theta. Of course, more than one, you can be saying L of vector theta the way you have been writing there. So in our case, in this example, L of theta equal function, so product f of xi semicolon theta. So we know f of x semicolon theta, so we just need to put I. So we are just putting I on x in equation 1.1. In equation 1.1, we are putting just I, the subscript I on x, which is basically that. We multiply this quantity. So you know what you do. Those having the same base, you sum the powers. So you sum the powers of xi here. But summation of xi is an x bar. If you come again, you sum the powers here. You sum 1 is n. You sum xi is an x bar. So it just be n into 1. So you'll have this is actually the likelihood function. This is a likelihood function. Get the log. And this log is to base e. This is a natural log. So when getting this log, I'm defining here in general, this is to base e. I don't have to indicate. So that, of course, we know. So when getting differentiation, you can get it easily. We could use another base, we shall get the same results, but they'll be longer. They'll be longer steps. So we use guided by the calculus, take it to base e, just use the natural log. So we have the log. So we have to look at we have to determine the point at which it is a maximum, just differentiate with respect to theta. So you can see here it is a full derivative because we only have one parameter. It's a full derivative. Why you was saying partial derivative here with respect to the H, you are saying when you are differentiating, if there are more than one parameter, or in general, you have k parameters, when you say differentiate partially with respect to the H, when you are differentiating with respect to the 1, you hold the other constant, you hold theta 2 up to theta k constant. When you are differentiating with respect to theta 2, you hold theta 1 and then theta 3, and theta 4 to theta k constant. That's what I meant by saying you differentiate partially. When there is one, it's a full derivative. So we only talk of partial when you have more than one. But when there is one, it's a full derivative. So we're just saying differentiate this log of L with respect to theta. So you are many. So this is the derivative. Remember methods of differentiation. Remember the chain rule. Remember whatever, all those rules, you know them. Equate to 0 and solve. After doing that, that is a solution. We have the MLE. In fact, in this example, it has yielded the same estimate as the method of moments. As I indicated earlier, the two methods can actually yield the same estimate in some cases. So for the Bernoulli, you find the method of moments estimate and the maximum likelihood estimate are the same. Example number 1, that was the case for one parameter. So the same will be done for any other with one parameter. You get the likelihood, get the log, differentiate full derivative, equate to 0, solve for the parameter, and that is your estimate. And again, once you have your estimate, you can readily write your estimator, just making it a random variable. Because we have said they are the same functionally. They are the same functionally. Example number 2. So in example number 2, we want to look at one with two parameters, and a very good candidate is the normal. We want to find maximum likelihood estimates of mu, sigma, and then by extension, there are only two parameters. Once we have estimates of mu and sigma, we are done. But we want to follow the same process and see, suppose we wanted to get an estimate for sigma squared, because we also did that for method of moments. We found an estimate for sigma, and also we found an estimate for sigma squared, which were basically solving the equation we were solving for sigma, and then in the next one we were solving for sigma squared. So we shall do exactly that. What happens here? Suppose I want to get for sigma, and I want to get for sigma squared. So again, we know the form of the distribution given by 1/4. The normal would mean mu, and finite sigma squared or standard deviation sigma. This is the likelihood. So you write the likelihood function as a function of the parameters. So the parameter in question now are the mu and sigma, the standard deviation, the one I'm highlighting. And that is the density. This is now the normal density. I'm multiplying out to get this. You multiply out. Remember, multiplying out, whatever you have a constant, you raise to n. Where you have a subscript in the power, you sum. You sum the power. It's exactly that. Take the log, natural log of this. You get that. Now we want to look for the point. So we need to differentiate this with respect to the first parameter, mu, partially. So when differentiating with respect to mu, you hold your sigma constant. That's what I meant. So when you do that, you equate to 0 and you solve, you find you already have now the estimate for mu. Mu hat is expo. Differentiate with respect to sigma partially. So you hold your mu constant. That is the derivative. You need to check. So what you are differentiating is this with respect to sigma. There's no sigma here, will go to 0. Here you are differentiating here and here with respect to sigma. This is a derivative. And you have equated to 0. I'm just solving. If you factor out 1 over sigma, you have 1 over sigma, and you have whatever you have in the large parenthesis, then you equate to 0. I'm just factorizing that result. But you know 1 over sigma cannot be 0. So what I have in the parenthesis is the one which must be 0. And if you equate what I have in the parenthesis equals to 0 and you solve for sigma, you actually get your sigma hat to be the standard deviation. As before, as the method of moments. So again, it yields the maximum likelihood estimate and the method of moments estimate. They are equal or they are the same. By extension, I wanted us to find, say, suppose I wanted for sigma squared. So I'll have to write L. I have to get log L mu. I like the parameter sigma squared. So it is basically the same function. The same function here. It's the same function here. But I'm looking at this. I want interested in sigma squared, not sigma. So I'm indicating here is sigma squared. So I'm interested in sigma squared. So unlike before, we were differentiating with respect to sigma. Now you have to differentiate this with respect to sigma squared. So you look at sigma squared like a parameter, you have to write if when you are differentiating, you look at sigma. So the derivative of log sigma squared will just be 1 over sigma squared, because you are looking at sigma squared just as a parameter. When you are differentiating this part, you have to write as sigma squared raised to minus 1. Then you differentiate with sigma squared will be minus 1, that's sigma squared, you subtract 1 raised to minus 2, like that. So if you differentiate this with respect to sigma squared, this is the derivative. You can factor out this quantity, and then you have what is in the large parenthesis, But whatever is factored out here cannot be 0. So it is what I have in the parentheses will be, you equate to 0. And when you equate to 0, and then you solve for sigma squared, that is your estimate. So you have our sigma squared hat, and you have our estimate. And if again you find that our sigma squared hat is a sum of variance. So also for this one, same as the method of moment estimates. And then what we note here, the estimate of sigma squared, which is sigma squared hat, is the square of the estimate of sigma. Sigma squared hat is equals to, remember sigma squared hat is the estimate of sigma squared, the population variance. And sigma hat is the estimate of population standard deviation. So you are saying here, we have found out that estimate of population variance, the sigma squared is sigma squared hat, is equals to the square of the estimate of population standard deviation. Because you can actually see here, sigma hat is S, but sigma squared hat is S squared. But I can write here S squared, but my S is sigma hat. So it's like saying sigma hat squared. So you can actually see that this process will locate, depending on what your parameter is, to locate the maximum. Now, I indicated before you look at the examples that for us to locate the maximum, we are basically utilizing the calculus. Of course, with the premise that the function, the likelihood function is continuous at the point, at the ML estimate. That is why calculus method will be able to locate that. But in situations where the function is not continuous at the point where it is a maximum, then calculus methods will not be able to locate that. It will fail. It will fail in the sense that at that point, well, I've been using the word continuous. I should be saying differentiable. Because for you to locate, you must differentiate, you equate to 0. A function can be continuous at a point, but not differentiable. So if it is not differentiable at the point where it is a maximum, then the calculus methods will not locate it. Simply put, a function is differentiable at a given point if you are able to throw a unique tangent to that curve or that function at that point. That is what calculus says. If it is not differentiable, you are not able to throw a unique tangent, then you cannot use calculus methods. So we have an advantage when it comes to when calculus methods works, but a disadvantage when calculus methods fail. But it will not help us. But when the calculus method fail, it does not mean that a maximum does not exist. It exists, but the only problem is that that function is not differentiable at that point. That is why I'm saying here, it is important to note that one must not always rely on the differentiation process to locate the maximum likelihood estimate of theta. If L of theta, there is a likelihood, is not differentiable at theta hat. That is now what you are trying to locate. We illustrate this case using the following two examples. Example number 1. So this has a continuation, not really. We have looked at two examples. So example number 3 is to address that possible scenario where we are saying an MLE exists, but the likelihood is not differentiable at the MLE. Uniform over the interval 0 theta. This is actually the function where I ask you to find the method of moments estimate. So this is actually the density. Uniform over that interval 0 theta. This is the density. But now our interest is to determine the MLE of theta here. And this is an early example where the method or moments estimate is actually different from the maximum likelihood estimate in this example. We already have the method or moment estimate. The one I said show. The one I said show. Was it what? 2x bar. I said show that. It was here. The one I said show inclusion 1 exercise. This one show that the method or moment estimate is theta hat 2x bar. So this is an example where the two we have seen for the binomial, they yield the same. For the normal, they yield the same. But this is an example where one, the method of the calculus methods fail to locate, and two, the two estimates using the two methods are different. So I've said I'll use two examples to illustrate that we can locate a maximum, we can locate the point at which the likelihood finds a maximum, but not using calculus methods because the function is not differentiable at that point. So for the uniform, this is a density, this is a likelihood function. And if you look at this likelihood function, this is a decreasing function of theta. No, this is 1 over theta, this has a constant. So you multiply a constant n times, is 1 over theta raised to n. And all the observations, you see the observation here, the observation is lies in the interval 0 theta. 0 otherwise. You see the PDF, it says 1 over theta, theta lies in that interval, and theta is positive, 0 otherwise. So also for the likelihood function, the observations, which we say product of xi theta. So the observations xi must lie in that interval because outside the function is 0. So if one of them now becomes 0, the whole thing will become 0. So we are saying that's why we say 0 otherwise. So all observations must lie in the interval 0 theta for it to be non-zero. That is why for all observations. So if you look at this function, you can see L theta over L is 1 over theta raised to n. N is a sample size. So you can see as you increase theta, because theta in the denominator has power n, so as you increase theta, L of theta decreases. No, that's why it is a decreasing function of theta. So as theta increases, L of theta decreases. So where is it a maximum? It is when theta must be small, because for large theta, L of theta is small. So we want for small theta, so that L of theta is large, because we want it where it is maximized. So the value of theta which maximizes L of theta is the smallest value satisfying. We want the smallest value of theta so that L of theta is a maximum. is the smallest value satisfying. So we want the smallest value and must satisfy this because all observations must be inside the interval. All observations must be inside the interval. But if all observations are inside the interval, these events that all observations are inside that interval 0 theta, these two events are actually equivalent that if I take the maximum, if the maximum lies between 0 and theta, it would imply that all of them lie in the interval. If the maximum lies between 0 and theta, that means all of them. Because if the maximum lie there, it will mean all of them will lie inside. So the two are equivalent. So we can actually write our likelihood function. So we are using this notation to indicate the maximum of these observations. So that if the maximum lies in that interval, then all of them are in the interval. So we can actually write our likelihood function not in terms of the observations, but in terms of the maximum, because this implies this and this implies this. So they are equivalent. If you have one, you have the other. And it's actually plausible. If all observations lie here, it means the maximum will lie there. If the maximum lies there, it means all of them are in there. So we can actually write the likelihood in terms of the maximum. So what it actually means here, we are saying the likelihood function, which you have said 1 over theta raised to n, now all observation lies in interval. Now we are now saying the maximum lie in that interval. So we have replaced this one by this because they are the same. So when you are saying 0 otherwise, we are actually saying it will be 0. So you can see that the maximum is less or equals theta. It only shall be having 1 over theta raised to n. Otherwise, it will be 0. Otherwise, it will mean when theta is less than the maximum. You know, here the maximum is less or equals theta. You know, but if theta is less than the maximum, it is the otherwise, it will be 0. Remember, we are looking for the value, the smallest value of theta. So that L of theta is a maximum. So if you look at theta here, the minimum value of theta is the maximum value. Otherwise, it can take bigger values because the maximum is less or equals theta. Theta is always greater than the maximum. Just the smallest value. The smallest value theta can take is the maximum. And other values greater than that. So the smallest, so we are actually saying theta is greater or equals to the maximum. So you can see the candidate values for theta starts from the maximum and even larger values of and larger values larger than the maximum. But I want now the smallest among those candidates. The smallest among those candidates will be the maximum. That will be by ML estimate. So my theta hat will be the maximum value. And you can see for the method of moments, theta, vector theta is 2x bar. You can see for this one, it is different from the method of moments estimate. So as indicated earlier, when the two methods give different estimates, in some remark, I indicated that usually ML estimates are superior in certain instances, and we will prefer the MLE to the method of moments estimate. So this example has illustrated two things. One, where the calculus method fails to locate the maximum, though it is there. Two, this is an example where it shows that the two methods yield different estimates, unlike the first two examples. So the whole idea is that L of vector theta is a maximum. However, L of theta is not differentiable at vector theta. What it actually means, if you are to draw this function, it's like an exponential. It goes exponential. It decays like exponentially. And where it is a maximum, if you are to draw, you'll find that it is not possible to draw a unique tangent at that point. It's actually at the end point. There's no, you have so many infinite number of lines. You cannot draw a unique tangent there. Meaning it's not differentiable at that point. So because it's not differentiable, it cannot be located by differentiation. That is why calculus method fails. You're almost done, and I'm getting a message saying somebody wants to join my meeting. I don't know, but we're almost done. So the second example is uniform over theta 1, theta 2. It was also there where I said determine the measure of moment estimates. This is actually the density. It's just what we did, like uniform over AB. A is theta 1, B is theta 2. We know the mean, the variance, and all kind of thing. This is where we are getting go to the likelihood function. That is the likelihood function. Again, it's a constant, you raise to n. All observations must lie there. And if you see this one, it is actually a decreasing function of this difference. If you look at this difference here, it's actually a decreasing function. As that difference increases, this function decreases. So it is a decreasing function of this difference. So when you want to maximize this function, you want the difference to be small. You want the difference to be small. Of course, when theta 2 minus 1 is very small, it will make this to be very large. So you can actually see that this event is the same as this event. We know if I take x1 to be the minimum observations and xn to be the maximum, you know the minimum is always less than the maximum, and they both lie in the interval. It will mean that all observations will lie there. If theta 1 is less or equal to the minimum, and the minimum is less than the maximum, and the maximum is less or equal to theta 2, it means all observations lie there. And conversely, if all observations lie in that interval, it will mean that it will also mean this. So you can actually write our likelihood function in terms of the minimum and the maximum. So instead of using this, I'll use this in terms of the minimum and the maximum. So when I say 0 otherwise, it is the other way around. You are saying minimum is less than theta 1. Here it is theta 1 is less or equal to the minimum. And also in our density, we know theta 1 is less than theta 2. But now here is the maximum is less or equal to theta 2. But now the other says theta 2 is less than the maximum. So this is what happens for when it will take 0. And when it takes 0, it means here an observation is outside the interval, theta 1, theta 2. So you can actually see that theta 1 is less or equals to the minimum. And the maximum is less or equals to theta 2. So you can see theta 1 starts from the minimum and goes to the left, whereas theta 2 starts from the maximum and goes to the right. And you are looking for when the difference theta 2 minus theta 1 is the smallest. This is the smallest when theta 2 is a maximum and theta 1 is a minimum. That is when the function will be maximized. and hence we have the estimates. These are the MLEs. We are not able to use here calculus methods, but these are the MLEs given by 2.27. And you can actually see, if you look at in that exercise where I said show, you'll find that the metal moments estimates and the MLEs are also different. In 5, I'm using it to illustrate that maximum likelihood estimates are not always unique also. And this example illustrates that. So you can have a look. That example, the way we had said also for metal moments estimates, they are not. Somebody saying, let me in, lost connection, but you're almost done. Somebody was logged out, but I think I've admitted that person. Yeah, sometimes the net can be erratic, but you're almost done anyway. So basically, that is the idea. Example number 5 illustrates that MLEs are not always unique. That means you can have more than one. And you can look at that example, that you can have more than one estimates. And maybe you can stop there. And now 2, 8, what, 8:47, almost 9. Maybe we can stop there, because what I wanted to say. So what the next part, which talks about inference property or maximum likelihood estimators, will illustrate actually the elegance of this method. You have seen that like for the normal, we look at for the normal where we wanted to we were differentiating with respect to sigma, and then we differentiate with respect to sigma squared. That idea can be handled in the MLEs using what we call the invariance property or maximum likelihood estimators by just imposing some condition. When dissatisfied, we can always deduce MLEs without necessarily going through some rigorous differentiation. One can avoid that by invoking this property, what we call invariance property or maximum likelihood estimators. And in particular, we shall consider the unidimensional case, say one parameter. So probably that is where we shall start with next week. And you can see so far, we have actually handled 2 methods. So we shall look at this property, and then we shall start our third method, which is Bayesian estimation. So, and I indicated in a remark that the MLEs and the Bayesian are related, somewhat related. So you must have understood very well this method so that we shall be able to relate to Bayesian. And meanwhile, understand your Bayes theorem in terms of probability distributions, because that is what we shall use in Bayesian. Understand your Bayes theorem very well, what we shall invoke that. So bye. Let me wish you a good evening and for your patience.
Thank you, Professor.
Karibu sana.